Thermodynamics, the movement of heat. We'll look at the relationship between energy and matter. The objectives for section 1, the flow of energy, heat, and work. 1. Explain how energy, heat, and work are related. Classify processes as either exothermic or endothermic. Third, identify the units used to measure heat transfer. And last, distinguish between heat capacity and specific heat. Key concepts for section 1. In what direction does heat flow? What happens in endothermic and exothermic processes? Third, in what units is heat flow measured? And last, on what two factors does the heat capacity of an object depend? The vocabulary, let's look at the pronunciation of these words. Surroundings, endothermic process, exothermic process, heat capacity, specific heat, chemical potential energy, law of conservation of energy, thermochemistry, heat, and system. Connecting to your world. Here is a volcano. A lot of dynamics going on here. Look at the lightning occurring because of all of the movement of air, water vapor, lava. It's quite amazing. Connecting to your world. Lava flowing out of an erupting volcano is very hot. Its temperature ranges from 550 to 1400 degrees Celsius. As lava flows down the side of a volcano, it loses heat and begins to cool slowly. In some instances, the lava may flow into the ocean, where it cools more rapidly. In this section, you will learn about heat flow and why some substances cool down or heat up more quickly than others. Connecting to your world. Let's do discuss and relate. Let's talk about volcano. We'll use the visual on the first page. What happens to the heat in lava once it flows out of a volcano? The heat is released. Why does lava cool more quickly in water than on land? Well, we will look and we will see that it has to do with greater capacity. Water has a greater capacity to absorb heat than does air. The temperature difference between the lava and water may be greater than between the lava and the air. Energy transformations. Energy is the capacity for doing work or supplying heat. Unlike matter, energy has neither mass nor volume. Energy is detected only because of its effects. For example, the motion of a race car in figure 17.1. Thermochemistry is the study of energy changes that occur during chemical reactions and changes in state. Every substance has a certain amount of energy stored inside it. The energy stored in the chemical bonds of a substance is called chemical potential energy. The kinds of atoms and their arrangement in the substance determine the amount of energy stored in the substance. And we've seen that in the last 16 chapters quite extensively. Word origins, exothermic. Exothermic comes from the Greek word exo, meaning outside of, or therm, meaning heat. Based on the characteristics of exothermic reactions, what do you think the Greek prefix endo means? Endo. The Greek prefix endo means within. Some examples of words that use this prefix are endoskeleton, endomorph, and endoderm. During a chemical reaction, a substance is transformed into another substance with a different amount of chemical potential energy. When you buy gasoline, you are actually buying the stored potential energy it contains. The controlled explosions of the gasoline in a car's engine transform the potential energy into useful work, which can be used to propel the car. At the same time, however, heat is also produced, making the car's engine extremely hot. Energy changes occur as either heat transfer or work, or a combination of both. Heat, represented by Q, is energy that transfers from one object to another because of a temperature difference between them. One of the effects of adding heat to an object is an increase in its temperature. It is the radiant heat of the sun's rays that makes a summer day hot. In this example, the air is the object that absorbs heat and increases its temperature. Heat always flows from a warmer object to a cooler object. If two objects remain in contact, heat will flow from the warmer object to the cooler object until the temperature of both objects is the same. Figure 17.1, when fuel is burned in a car engine, chemical potential energy is released and is used to do work. Very exciting. Figure 17.1, let's discuss and relate. Energy transformations. Have students study the photograph of the race car. All right, study the car. What work is done as the chemical potential energy of the fuel is released? The race car moves around the track. All right, very quickly. In addition to work, what other types of energy change occurs as the fuel is burned? Heat is released. Exothermic and endothermic processes. Discuss with students the distinction between kinetic and potential energy. Kinetic energy is the energy associated with an object because of its motion. Potential energy is the energy associated with an object because of its position in a field of force or due to its particular chemical composition. Explain that the potential energy of a reactant or a product in a chemical reaction is determined by the strengths of the attractive and repulsive forces between atoms. In a chemical reaction, atoms are rearranged into new groupings that have different relative potential energies. The change in potential energy is either the result of absorption of energy from the surroundings, endothermic reaction, or the release of energy to the surroundings, exothermic reaction. Exothermic and endothermic processes. Chemical reactions and changes in physical state generally involve either the release or the absorption of heat. In studying energy changes, you can define a system as the part of the universe on which you focus your attention. The surroundings include everything else in the universe. In thermochemical experiments, you can consider the region in the immediate vicinity of the system as the surroundings. Together, the system and its surroundings make up the universe. A major goal of thermochemistry is to examine the flow of heat between the system and its surroundings. Together, the system and its surroundings make up the universe. A major goal of thermochemistry is to examine the flow of heat between the system and its surroundings. Units for measuring heat flow. Discuss. Make sure students understand the terms introduced in this section and how to convert from one to another. Students may have difficulty with the distinction between calorie with a small c and calorie with a capital C. because everyday usage of the terms is often not accurate. The distinction between heat capacity and specific heat can be hard to remember because the terms are so closely related and sound so similar. Tell students to remember that specific heats of different materials can be compared because the quantity of matter involved, 1 gram, is specific. The law of conservation of energy states that in any chemical or physical process, energy is neither created nor destroyed. If the energy of the system decreases during that process, the energy of the surroundings must increase by the same amount so that the total energy of the universe remains unchanged. In thermochemical calculations, the direction of the heat flow is given from the point of view of the system. An endothermic process is one that absorbs heat from the surroundings. In an endothermic process, the system gains heat as the surroundings cool down. In figure 17.2a, the system, the person, gains heat from its surroundings, the fire. So when you talk about heat or hot and cold, hot is when the hand or the body absorbs heat. Cold is when it releases heat. So hot and cold is basically a human feeling. When I mean feeling like nerves, when energy crosses the skin going from the body to the outside, and the heat crosses those nerve endings going in that direction, it feels cold. When it's coming into the body, it feels hot. More on that later. Heat flowing into a system from its surroundings is defined as positive. Q has a positive value. An exothermic process is one that releases heat to its surroundings. In an exothermic process, the system loses heat as the surroundings heat up. In figure 17.2b, the system, the body, loses heat to the surroundings, the perspiration on the skin and the air. Heat flowing out of a system into its surroundings is defined as negative. Q has a negative value because the system is losing heat. What does the law of conservation of energy state? The law of conservation of energy states that in any chemical or physical process, energy is neither created nor destroyed. Now remember, from the body's point of view, when you're cold, that's exothermic. The body is losing heat. When you're hot, that's endothermic. The body is gaining heat. When you sweat, you're getting rid of that excess heat. You're trying to cool down. So the sweating is exothermic. So you can think of it in a sense that you have this equilibrium between heating and cooling relative to the body. Heat flow is defined from the point of view of the system. A, in an endothermic process, heat flows into the system from its surroundings. You're cold and you're trying to warm up. The fire is warming you. In an exothermic process, heat flows from the system to its surroundings. You're sweating. You're trying to get rid of that heat. In both cases, energy is conserved. Interpret the diagrams. In which process does Q have a negative value? In the process shown in figure 17.2b, the system loses heat to its surroundings, so Q is negative. Units for measuring heat flow. Describing the amount of heat flow requires units different from those used to describe temperature. Heat flow is measured in two common units, calorie and joule. You have probably heard of someone exercising to burn calories. During exercise, your body breaks down sugars and fats into carbon dioxide and water, and this process releases heat. Although there is not an actual fire burning the sugars and fats within your body, chemical reactions accomplish the same thing. In breaking down 10 grams of sugar, for example, your body releases a certain amount of heat. The same amount of heat would be released if 10 grams of sugar were completely burned in fire. So you can see that this calorie thing is a little bit difficult to nail down. A calorie, small c, is defined as the quantity of heat needed to raise the temperature of 1 gram of pure water 1 degree Celsius. The word calorie is written with this small c except when referring to the energy contained in food. The dietary calorie, capital C, written with a capital C, always refers to the energy in food. 1 dietary calorie is actually equal to 1 kilocalorie, or 1,000 small c calories. So 1 capital C calorie equals 1 kilocalorie equals 1,000 small c calories. The statement 10 grams of sugar has 41 capital C calories means that 10 grams of sugar releases 41 kilocalories of heat when completely burned. The joule is the SI unit of energy. 1 joule of heat raises the temperature of 1 gram of pure water 0.2390 degrees Celsius. You can convert between calories and joules using the following relationships. 1 joule equals 0.230 calories, and 4.184 joules equals 1 calorie. A massive steel girder has a higher heat capacity than a steel nail. Inferring, what factors affect how quickly the different areas of construction site will heat up during the day? The lower the specific heat capacity of an object, the more quickly it will heat up. Also, obviously, color has something to do with it. The darker colored objects will heat up more quickly than the more neutral or lighter colored objects. Heat capacity and specific heat. The amount of heat needed to increase the temperature of an object exactly 1 degree Celsius is the heat capacity of that object. The heat capacity of an object depends on both its mass and its chemical composition. The greater the mass of the object, the greater its heat capacity. One of the massive steel girders in figure 17.3, for example, requires much more heat to raise its temperature 1 degree Celsius than a small steel nail does. Similarly, a cup of water has a much greater heat capacity than a drop of water. Different substances with the same mass have different heat capacities. Table 17.1, discuss and relate. Use visuals, heat capacity and specific heat. Have students study table 17.1, which has a higher specific heat capacity, water or steam. Water. What factors do you think affect the specific heat of each substance? Specific heat is affected by the amount of heat and the change in temperature. Look at the definition of specific heat. Here's table 17.1 and some specific heat capacities in joules per gram degree Celsius and small c calories per gram degree Celsius. Look at iron and look at water and how different it is. On a sunny day, a 20 kilogram puddle of water may cool, while a nearby 20 kilogram iron sewer cover may be too hot to touch. This situation illustrates how different heat capacities affect the temperature of objects. Assuming that both the water and the iron absorb the same amount of radiant energy from the sun, the temperature of the water changes less than the temperature of the iron because the specific heat capacity of the water is larger. The specific heat capacity, or simply specific heat, of a substance is the amount of heat it takes to raise the temperature of 1 gram of a substance 1 degree Celsius. Table 17.1 gives specific heats for some common substances. Water has a very high specific heat compared with that of other substances, especially iron, in the table. You can see from the table that 1 calorie of heat raises the temperature of 1 gram of water 1 degree Celsius. Metals, however, have low specific heats. 1 calorie of heat raises the temperature of 1 gram of iron 9 degrees Celsius. So water has a specific heat 9 times that of iron. The same amount of heat affects the temperature of objects with a high specific heat much less than temperature of those with low specific heat. Water releases a lot of heat as it cools. During freezing weather, farmers protect citrus crops by spraying them with water. The ice that forms has a protective effect as long as its temperature does not drop below 0 degrees Celsius. B, because it is mostly water, the filling of a hot apple pie is much more likely to burn your tongue than the crust. Figure 17.4, thinking critically. Show students a map of California and discuss the difference in temperature between a coastal city, such as San Francisco, and an inland city, such as Fresno. Ask students to explain a remark once made by Mark Twain. The coldest winter I ever spent was a summer I spent in San Francisco. Use visuals, thinking critically. The relatively high heat capacity of large bodies of water near San Francisco helped to moderate local temperatures. During summer, the ocean water warms slowly as it absorbs large amounts of heat from warm air masses. Onshore breezes off the cool water keep coastal land temperatures from rising to match those of inland areas. Condensation of water vapor in the air produces a cool fog, which probably enhanced Mark Twain's impression of the cool of San Francisco's summers. Figure 17.4, let's continue, discuss and relate using visuals. Have students refer to figure 17.4. Discuss how spraying fruit and flooding orchards with a few inches of water can keep the fruit from freezing. As water cools and freezes, it releases energy that can warm the air and protect the fruit. Just as it takes a lot of heat to raise the temperature of water, water also releases a lot of heat as it cools. Water in lakes and oceans absorb heat from the air on hot days and releases it back into the air on cool days. This property of water is responsible for moderate climates in coastal areas. 17.4 illustrates two other common effects associated with the high specific heat of water. The orange trees in figure 17.4a have been sprayed with water to protect the fruit from frost damage during icy weather. As the water freezes, it releases heat, which helps prevent the fruit from freezing. In figure 17.4b, the label on a box of apple pie warns that the filling is hot, and people still will ignore that and get burned. When a freshly baked apple pie comes out of the oven, both the filling and the crust are at the same temperature. However, the filling, which is mostly water, has a high specific heat, higher specific heat than the crust. In order to cool down, the filling must give off a lot of heat. This is why you have to be careful not to burn your tongue when eating hot apple pie. To calculate the specific heat of a substance, you divide the heat input by the temperature change times the mass of the substance. C equals Q over M delta T, or heat, joules, or calories, or capital C calories, divided by mass and divided by change in temperature. In the equation above, Q is heat and M is mass. The symbol delta T, read delta T, represents the change in temperature. Delta T is calculated from the equation delta T equals Tf minus Ti, where Tf is the final temperature and Ti is the initial temperature. As you can see from the equation, specific heat may be expressed in terms of joules or calories. Therefore, the units of specific heat are either joules over gram degree Celsius or calories over gram degree Celsius. What is the relationship between specific heat and heat capacity? The specific heat is the heat capacity of an object divided by its mass in grams. Dietary calories. Your proper caloric intake depends on your level of physical activity. In an 8-hour day at a desk, you burn about 800 calories. This is about the number of calories, capital C, in 2 helpings of spaghetti. When exercising, however, you become a relative biochemical blast furnace. In vigorous activities such as running and jumping, you expend 7 to 10 calories per minute, or 420 to 600 calories per hour. At these rates, a runner who covers 26-mile marathon course in 3 hours might expend 1,800 calories, or the equivalent of 4.5 helpings of spaghetti. Have students do research to compare the energy expended in calories per minute during several types of sports-related and non-sports-related activities. Objective, Section 2. Describe how calorimeters are used to measure heat flow. Construct thermochemical equations. Solve for enthalpy changes in chemical reactions. Key concepts. What basic concepts apply to calorimetry? How can you express the enthalpy change for a reaction in a chemical equation? Here's some vocabulary. Let's look at the pronunciation. Calorimetry, calorimeter, enthalpy, thermochemical equation, heat of reaction, heat of combustion, connecting to your world. As you know, a burning match gives off heat. When you strike a match, heat is released to the surroundings in all directions. You can classify this reaction as exothermic. In addition to describing the direction of heat flow, you may also want to determine the quantity of heat that is transferred. How much heat does a burning match release to the surroundings? In this section, you will learn how you can measure heat flow in chemical and physical processes by applying the concept of specific heat. Calorimetry. Heat that is released or absorbed during many chemical reactions can be measured by a technique called calorimetry. Calorimetry is the precise measurement of the heat flow into or out of a system for chemical and physical processes. In calorimetry, the heat released by the system is equal to the heat absorbed by its surroundings. Conversely, the heat absorbed by a system is equal to the heat released by its surroundings. The insulated device used to measure the absorption or release of heat in chemical or physical processes is called a calorimeter. A calorimeter. In a simple constant pressure calorimeter, a thermometer records the temperature change as chemicals react in water. The substance reacting in solution constitute the system. The water constitutes the surroundings. Calorimetry, discuss and relate. In this one, we're going to simply relate. Show students typical utility bills for electricity, gas, or oil. Why would the size of the bill vary from one household to another? Floor space, number of occupants, thermostat settings, insulation, type of fuel used. Why might the bill vary from month to month? Changes in the gradient between internal and external temperatures, fluctuations in fuel prices. That simply means that some months are hotter or cooler than others. Constant pressure calorimeters. Foam cups are excellent heat insulators because they do not let much heat in or out. They are adiabatic. They can be used as simple calorimeters. In fact, the heat flows for many chemical reactions can be measured in a constant pressure calorimeter, similar to the one shown in figure 17.5. Because most chemical reactions and physical changes carried out in the laboratory are open to the atmosphere, these changes occur at constant pressure. The heat content of a system at constant pressure is the same as a property called enthalpy, that's capital H, enthalpy of the system. The heat released or absorbed by a reaction at constant pressure is the same as the change in enthalpy, symbolized as delta H. And that's adiabatic. Adiabatic means that it's insulated. It's a shield against heat flow. Because the reactions presented in this textbook occur at constant pressure, the terms heat and enthalpy change are used interchangeably. In other words, Q equals delta H. To measure the enthalpy change for a reaction in aqueous solution in a foam cup calorimeter, you dissolve the reacting chemicals, the system, in known volumes of water, the surroundings. Then measure the initial temperature of each solution and mix the solutions in the foam cup. After the reaction is complete, measure the final temperature of the mixed solutions. Because you know the initial and final temperature and the heat capacity of water, you can calculate the heat absorbed by the surroundings, Q sub SURR, using the formula for specific heat. Q surroundings equals MTC. That's the heat of the surroundings equals the mass times the temperature times the specific heat capacity. In this expression, M is the mass of the water, C is the specific heat of water, and delta T equals TF minus TI, because the heat absorbed by the surroundings is equal to, but has the opposite sign of, the heat released by the system. The enthalpy change for the reaction delta H can be written as follows. Q system equals delta H equals negative Q surroundings equals negative M delta T C. The sign of H is negative for an exothermic reaction and positive for an endothermic reaction. Now let's look at a calorimeter. Its nutritionists use bomb calorimeters to measure the heat content of the foods you eat. Let's take a look at it very quickly. You can see inside there is a chamber that will burn the food. Now, this heat will be transferred to the water that surrounds it. And then the temperature change can be read, and the heat released by the burning of the food can be calculated. Discuss, if possible, show photographs or actual examples of the types of calorimeters used in laboratories today. Discuss the use of calorimetry as an analytical tool. For example, in investigating the caloric content of foods, make sure students understand all the terms in the equation Q system equals delta H equals negative M times C times delta T. Emphasize that the delta notation represents an algebraic operation involving two separate measurements. When determining the algebraic value of delta T, the algebraic sign of the final and initial temperatures must be included in the operation. That's very important and the source of most error in these kinds of calculations. 17.6. Nutritionists use bomb calorimeters to measure the energy content of foods you eat. To see some of their data expressed in calories per serving, you can look at a nutritional label, calculating. According to the nutritional label below, each serving contains 140 calories. How many kilojoules is this? A simple conversion will give you 586 kilojoules. Constant volume calorimetry experiments can also be performed at constant volume using a device called a bomb calorimeter. In a bomb calorimeter shown in figure 17.6, a sample of a compound is burned in a constant volume chamber in the presence of oxygen at high pressure. The heat that is released warms the water surrounding the chamber. By measuring the temperature increase of the water, it is possible to calculate the quantity of heat released during the combustion reaction. What formula is used to calculate the enthalpy change in a constant pressure calorimeter? Q system equals delta H equals negative Q surroundings equals negative M delta T C. Thermochemical equations. If you mix calcium oxide with water, the water in the mixture becomes warm. This exothermic reaction occurs when cement, which contains calcium oxide, is mixed with water to make concrete. When 1 mole of calcium oxide reacts with 1 mole of water, the 1 mole of calcium hydroxide forms and 65.2 kilojoules of heat is released. In a chemical equation, the enthalpy change for the reaction can be written as either a reactant or a product. In the equation describing the exothermic reaction of calcium oxide and water, the enthalpy change can be considered a product. That's calcium oxide plus water yields calcium hydroxide plus 65.2 kilojoules. Figure 17.7, these enthalpy diagrams show exothermic and endothermic processes, the reaction of calcium oxide in water, and the decomposition of sodium bicarbonate. Study these very, very carefully. They will be very helpful. Identify, in which case is the enthalpy of the reactants higher than that of the products? For the exothermic reaction, 1 mole of calcium oxide plus 1 mole of water yields 1 mole of calcium hydroxide. Thermochemical equations. Discuss and relate. Discuss, to illustrate writing a thermochemical equation, refer to two familiar reactions. The combustion of methane in a Bunsen burner adds energy to the surroundings. Thus, the burning of methane has a negative delta H. 1 mole of methane plus 2 moles of oxygen yields 1 mole of carbon dioxide plus 2 moles of water plus 890 kilojoules. That's negative 890 kilojoules per mole of methane. During the electrolysis of water, electrical energy is used to decompose the water into hydrogen gas and oxygen gas. Energy is added to the system from the surroundings. Thus, the electrolysis of water has a positive delta H. A positive delta H. Let's look at that more closely. So you have 241.8 kilojoules per mole plus 2 moles of water. That will decompose into 2 moles of hydrogen plus 1 mole of oxygen. So it's endothermic by 241.8 kilojoules per mole. Remind students that the sign of the delta H indicates whether the reaction is endothermic or exothermic. Although by convention an exothermic reaction is a negative delta H, when heat is shown as a product in an equation, it is expressed as an absolute value. Figure 17.7, discuss and relate. Use visuals. Draw similar diagrams for the burning of methane and the electrolysis of water. For each reaction, ask, is the potential energy of the reactants higher or lower than the products? Higher for methane, lower for water. Therefore, water would be more stable. In what direction does heat move in diagram 17.7a? Into the surroundings. In what direction does it move in 17.7b? Absorbed from the surroundings by the reaction or into the system. This equation is presented visually in figure 17.7a. A chemical equation that includes the enthalpy change is called a thermochemical equation. The heat of reaction is the enthalpy change for the chemical equation exactly as it is written. You will usually see heats of reaction reported as H, which is equal to the heat flow at constant pressure. The physical state of the reactants and products must also be given. The standard conditions are that the reaction is carried out at 101.3 kilopascals, 1 atmosphere, and that the reactants and products are in their usual physical states at 25 degrees Celsius. The heat of reaction, or H, in the above example is 65.2 kilojoules. Each mole of calcium oxide and water that react to form calcium hydroxide produces 65.2 kilojoules of heat. Calcium oxide plus water yields calcium hydroxide plus 65.2 kilojoules. Other reactions absorb heat from the surroundings. For example, baking soda, sodium bicarbonate, decomposes when it is heated. The carbon dioxide released in the reaction causes a cake to rise while baking. This process is endothermic. That is, 2 moles of sodium bicarbonate plus 129 kilojoules yields 1 mole of sodium carbonate plus 1 mole of water plus 1 mole of carbon dioxide. Remember that H is positive for endothermic reactions. Baking soda, relate. The decomposition of sodium bicarbonate to form carbon dioxide gas is essential for successful baking. Sodium bicarbonate is called baking soda, is the source of carbon dioxide that causes cakes, muffins, and quick breads to rise in the oven. Without this substance, these foods would be flat and heavy. Therefore, you can write the reaction as follows. 2 moles of sodium bicarbonate yields 1 mole of sodium carbonate plus 1 mole of water plus 1 mole of carbon dioxide, and the delta H is 129 kilojoules. That's endothermic. Figure 17.7b shows the enthalpy diagram for this reaction. Chemistry problems involving enthalpy changes are similar in stoichiometry problems. The amount of heat released or absorbed during a reaction depends on the number of moles of reactants involved. The decomposition of 2 moles of sodium bicarbonate, for example, requires 129 kilojoules of heat. Therefore, the decomposition of 4 moles of the same substance would require twice as much heat, or 258 kilojoules. In this and other endothermic processes, the potential energy of the products is higher than the potential energy of the reactants. The physical state of the reactants and products in a thermochemical reaction must also be stated. To see why, compare the following 2 equations for the decomposition of 1 mole of water. 1 mole of water, liquid, yields 1 mole of hydrogen gas plus 1/2 mole of oxygen gas, and that has an enthalpy of 285.8 kilojoules. That's endothermic. 1 mole of water gas yields 1 mole of hydrogen plus 1/2 mole of oxygen, and that's 241.8 kilojoules, and that's also endothermic. That's a difference of 44.0 kilojoules. That's substantial. Although these 2 equations are very similar, the different physical states of water results in different H values. In one case, the reactant is a liquid. In the other case, the reactant a gas. The vaporization of 1 mole of liquid water to water vapor at 25 degrees Celsius requires an extra 44 kilojoules of heat. Water liquid to water gas is additionally endothermic and requires 44 kilojoules. Checkpoint. Why must the physical state of the reactants and products be stated in a thermochemical equation? Different physical states of the same substance have different delta H values. They also have different specific heat values as well. Here is table 17.2, heats of combustion for various substances. The combustion of natural gas is an exothermic reaction, as bonds in methane, the main component of natural gas, and oxygen are broken and bonds in carbon dioxide and water are formed, large amounts of energy are released. Table 17.2 lists heats of combustion for some common substances. The heat of combustion is the heat of reaction for the complete burning of 1 mole of a substance. The combustion of natural gas, which is mostly methane, is an exothermic reaction used to heat many homes around the country. 1 mole of methane plus 2 moles of oxygen yields 1 mole of carbon dioxide plus 2 moles of water plus 890 kilojoules. That's exothermic. You can also write this equation as follows. 1 mole of methane plus 2 moles of oxygen gas yields 1 mole of carbon dioxide gas plus 2 moles of water liquid, and then put the delta H equals negative 890 kilojoules. Burning 1 mole of methane releases 890 kilojoules of heat. The heat of combustion, H, for this reaction is 890 kilojoules per mole of carbon burned. Keeping warm. How do animals such as polar bears and seals survive the cold land and water temperatures where they live? A good coat of fur helps, but it is not enough to keep them warm. These animals also have unique fat cells that help generate heat. These fat cells are in tissues called brown fat. The cells of brown fat are unlike other fat cells in these animals' bodies. Most other cells store chemical energy released during the breakdown of carbohydrates and fatty acids in bonds of adenosine triphosphate, ATP. ATP acts as the central source of energy and growth of all organisms. Heat is mostly a waste product in ATP producing cells. The heat generated by the brown fat tissue, however, helps the animal keep relatively comfortable even at sub-zero temperatures. Like other heats of reaction, heats of combustion are reported as the enthalpy changes when the reactions are carried out at 101.3 kilopascals of pressure, 1 atmosphere, and the reactants and products are in their physical states at 25 degrees Celsius. Section 3, heat in changes of state. Classify the enthalpy change that occurs when a substance melts, freezes, boils, condenses, or dissolves. Solve for the enthalpy change that occurs when a substance melts, freezes, boils, condenses, or dissolves. Key concepts: heat in changes of state. How does the quantity of heat absorbed by a melting solid compare to the quantity of heat released when the liquid solidifies? How does the quantity of heat absorbed by a vaporizing liquid compare to the quantity of heat released when the vapor condenses? And what thermochemical changes can occur when a solution forms? Some vocabulary, work on the pronunciation. Molar heat of fusion, molar heat of solidification, molar heat of vaporization, molar heat of condensation, molar heat of solution. Connecting to your world. An athlete can burn a lot of calories during a race. These calories are either used to do work or are released as heat. When your body heats up, you start to sweat. The evaporation of sweat is your body's way of cooling itself to a normal temperature. This section will help you to understand how the evaporation of sweat from your skin helps to rid your body of excess heat. Connecting to your world, discuss and relate. Use visuals, evaporation. Remind students that evaporation is a physical change from a liquid state to a gas or vapor. Question: on a molecular level, what is the difference between liquid water and water vapor? In the vapor phase, the water molecules are farther apart and not as strongly attached to each other. Because of the attraction between molecules in liquid, what must happen for a liquid to change into a gas? Energy must be added to overcome the attraction. Is evaporation endothermic or exothermic? Is evaporation endo or exothermic? It is endothermic. Heats of fusion and solidification. What happens if you place an ice cube on a table in a warm room? The ice cube in the system and the table and air around it are the surroundings. The ice absorbs heat from its surroundings and begins to melt. The temperature of the ice and water produced remains at 0 degrees Celsius until all the ice has melted. The temperature of the water begins to increase only after all of the ice has melted. Like ice cubes, all solids absorb heat as they melt to become liquids. The gain of heat causes a change of state instead of a change in temperature. Whenever a change of state occurs by a gain or loss of heat, the temperature of the substance undergoing the change remains constant. Enthalpy changes accompany changes in state. Fusion and vaporization are endothermic processes. Solidification and condensation are exothermic processes. Interpreting diagrams. Which arrows represent processes that release heat to the surroundings? That is solidification and condensation. The heat absorbed by 1 mole of a solid substance as it melts to a liquid at a constant temperature is the mole of heat of fusion, or delta H sub FUS. The molar heat of solidification, delta H solid, is the heat lost when 1 mole of a liquid solidifies at a constant temperature. The quantity of heat absorbed by a melting solid is exactly the same as the quantity of heat released when the liquid solidifies. That is, delta H fusion equals negative delta H solid, or solidification. This relationship is shown in figure 17.9. The melting of 1 mole of ice at 0 degrees Celsius to 1 mole of water at 0 degrees Celsius requires the absorption of 6.01 kilojoules of heat. The quantity of heat is the molar heat of fusion of water. Likewise, the conversion of 1 mole of water at 0 degrees Celsius to 1 mole of ice at 0 degrees Celsius releases 6.01 kilojoules. This quantity of heat is the molar heat of solidification of water as illustrated in the equations below. Here is table 17.3, heats of physical change. Notice the difference in the heat of fusion and the heat of vaporization for water. It's pretty large difference. Heats of vaporization and condensation. When liquids absorb heat at their boiling points, they become vapors. The amount of heat necessary to vaporize 1 mole of a given liquid is called the molar heat of vaporization, or delta H VAP. Table 17.3 lists the molar heats of vaporization for several substances at normal boiling points. The molar heat of vaporization of water is 40.7 kilojoules per mole. This means that it takes 40.7 kilojoules of energy to convert 1 mole of water molecules in the liquid state to 1 mole of water molecules in the vapor state at normal boiling points of water. That's 100 degrees Celsius at 1 atmosphere, or 101.3 kilopascals. This process is described in the thermochemical equation below. Diethyl ether, C4H10O, is the low boiling point liquid. BP is negative 34.6 degrees Celsius. That is a good solvent and was formerly used as an anesthetic. If diethyl ether is poured into a beaker on a warm, humid day, the ether will absorb heat from the beaker walls and evaporate very rapidly. If the beaker loses enough heat, the water vapor in the air may condense and freeze on the walls of the beaker. If so, a coating of frost will form on the outside of the beaker. Diethyl ether has a molar heat of vaporization of 15.7 kilojoules per mole. Condensation is the exact opposite of vaporization. When a vapor condenses, heat is released. The amount of heat released when 1 mole of vapor condenses at the normal boiling point is called its molar heat of condensation. This value is numerically the same as the corresponding molar heat of vaporization. However, the value has the opposite sign. The quantity of heat absorbed by a vaporizing liquid is exactly the same as the quantity of heat released when the vapor condenses. That is, delta H vaporization equals negative delta H condensation. Using the heat of fusion in phase change calculations, how many grams of ice 0 degrees Celsius will melt if 225 kilojoules of heat are added? That's the heat of fusion equals 6.01 kilojoules per mole. That's going to be the constant. And that's going to equal 225 kilojoules over X moles. I'm using proportional relationships here. It's easier. So X is going to be 0.374 moles. Now set up another proportional relationship. So you have water, 18 grams per mole. So that's another constant. And then 18 grams per mole over X grams over 0.374 moles. And X will equal 6.73 grams. So that's the answer to the question. Here is 17.10. Please study it carefully. The heating curve graphically describes the enthalpy changes that take place during phase changes. Figure 9, visual strategy. Identify which region of the graph is temperature constant. Which regions are temperature constant? At the melting point and boiling point, the horizontal areas. Describe how does the amount of energy required to melt a given mass of ice compare to the energy required to vaporize the same mass. It takes much less energy to melt a given mass of ice than to vaporize the same mass of water. The delta H of fusion is much smaller than the delta H of vaporization. Which region of the graph represents the coexistence of solid and liquid, liquid and vapor? The plateau of the curve between solid and liquid, the plateau between liquid and vapor. Enrichment question. How would the rate of heating affect the heating curve? The faster the rate of heating, the steeper the slope of the curve will be. Figure 17.10 summarizes the enthalpy changes that occur as a solid is heated to a liquid and then to a vapor. You should be able to identify certain trends regarding the temperature during changes of state and the energy requirements that accompany these changes from the graph. The large values of delta H vaporization and delta H of condensation are the reason hot vapors such as steam can be very dangerous. You can receive a scalding burn from steam when the heat of condensation is released as the steam touches your skin. That is water gas to water liquid with the delta H of condensation of negative 40.7 kilojoules per mole. What is the molar heat of vaporization? The faster the rate of heating is, the steeper the slope of the curve will be. Ether. Before the mid-1840s, patients undergoing surgery received no anesthesia, and they had to endure intense pain. Then, anesthesia properties of diethyl ether, commonly called ether, and chloroform were discovered. By the Civil War, use of these two substances was common. When available, they were used in surgeries on the battlefield. Anesthetics were generally applied by pouring the agent on linen, holding it at some distance above the patient's nose and mouth for the first inhalation, and then gradually moving the cloth closer until the desired effects were produced. Ether is no longer used as an anesthetic because it is flammable and causes many undesirable side reactions in patients. Figure 17.11, discuss and relate. Use visuals, heat of solutions. Have students look at the photo of a cold pack. Is the process that occurs in a cold pack endo or exothermic? It's endothermic. How do you know? Heat is absorbed and the temperature of the surroundings decreases. The surroundings is where you're applying the cold pack to. If it's your leg, then the surroundings is your leg, and you're warming the system using heat from your body. When heat leaves your body, that feels cold. So you're heating the system using the surroundings, and your surroundings is your leg. In which direction is heat flowing? From the surroundings, your leg, to the system. Is the process in the hot pack endothermic or exothermic? It's exothermic. It's giving off heat, so it would warm your leg. How do you know? Because your leg is the surroundings and your leg would gain heat. Heat is released and the temperature of the surroundings increases, and your wound or your leg would be the surroundings. In which direction is the heat flowing? From the system to the surroundings. Heat of solution. If you've ever used a hot pack or a cold pack, then you have felt the enthalpy changes that occur when a solute dissolves in a solvent. During the formation of a solution, heat is either released or absorbed. The enthalpy change caused by dissolution of 1 mole of substance is the molar heat of solution. So sodium hydroxide provides a good example of an exothermic molar heat of solution. When 1 mole of sodium hydroxide, NaOH, is dissolved in water, the solution can become so hot that it steams. The heat from this process is released as the sodium ions of the hydroxide ions interact with the water. The temperature of the solution increases, releasing 445.1 kilojoules of heat as the molar heat of solution. 1 mole of sodium hydroxide yields 1 mole of sodium ions and 1 mole of hydroxide ions. And the heat of the solution is exothermic, or a negative 445.1 kilojoules per mole. A practical application of exothermic dissolving is a hot pack. A hot pack mixes calcium chloride, CaCl2, and water, which produces the heat characteristic of an exothermic reaction. Calcium chloride, 1 mole of calcium chloride yields 1 mole of calcium ions and 2 moles of chlorine ions, and a exothermic delta H of solution of 82.8 kilojoules per mole. The dissolution of ammonium nitrate, NH4NO3, is an example of an endothermic process. The cold pack shown has 2 sealed plastic bags, one inside the other. The outer bag contains ammonium nitrate crystals. The inner bag contains liquid water. When the pack is squeezed, the inner bag breaks, allowing the ammonium nitrate and water to mix. Inferring, how would you define the system and the surroundings in this process? The system is the cold pack. The athlete and the air around the cold pack constitute the surroundings. When ammonium nitrate dissolves in water, the solution becomes so cold that frost may form on the outside of the container. Instant cold packs, which are used to treat muscle aches and sore joints to reduce inflammation, work by endothermic dissolving. The cold pack in figure 17.11 contains solid ammonium nitrate crystals and water. Once the solute dissolves in the solvent, the pack becomes cold. In this case, the solution process absorbs energy from the surroundings. So 1 mole of ammonium nitrate yields 1 mole of ammonium ions and 2 moles of chloride ions. What is the molar heat of solution? The enthalpy changes caused by dissolution of 1 mole of a substance.